So I hope that some of the old timers will remember me from back in the day. So Splash 2014 or so, I just finished a project monitoring metric temporal logic, and didn't quite know what to do with it. It was sort of fine, but if you were monitoring something that was going over a network, something like that, it was easy to say, all right, I'll tie to that. But I felt like it could be used for some, just internal performance, or I guess requirements. And then I really had this problem of when relationships exist between multiple entities that don't know about each other, you can create a monitor, but then how do you make sure that you know when to kill it at the right time? And so then, there were all these presentations about this thing called Rescala and distributed Rescala, even better. And it sort of inspired me to think that there might be a way to have a declarative language that would somehow make it possible to get these things in. I'll just give away the ending. I haven't gotten to that part yet. I had several detours along the way. At my work, so I work at Southwest Research Institute in addition to being a student at UTSA, a very slow PhD student. And there we used Qt, and we had some very complicated applications that did need to be dynamic. In response to some event, they'd rewire the dependencies. But where that happened in the code was kind of up to when the person who was assigned to do the job thought they might like to do it. So they'd set up some kind of a listener and an event fires, and now you're in a different file from where the original flows were set up. And so I didn't care for that. And I think the same problem really does exist for the reactive extensions as well, even though they were quite popular. And it did come back, I think, 1 year later to try to propose and demonstrate how you could use metric temporal logic as an operator inside reactive extensions. But at the same time, it's not glitch-free. And that glitch freedom thing that was being touted for the Rescala and the distributed Rescala was pretty exciting to me. So I returned to it, but being where I work and whatnot, I decided not to go with Scala. So the opposite decision of our keynote presenter. And so there was this other implementation out there, SodiumFRP, and it ended up informing a lot of my decisions about how I would actually approach things. But the problem, as I saw it, was that, and I don't think there's any debate in this room, that people have a hard time reasoning about what reactive programming or programs are going to do. But in my experience, and maybe this room differs, but normal programmers maybe tend to prefer the non-glitch-free frameworks. They the reactive extensions are really popular. As I said, it's easy to get started on the previous slide, but then you don't end up, I feel, in as sound of a space. So my goal is to provide a glitch-free reactive system and I worked really hard on this term. It said legacy at first, but imperative experienced programmers seems kinder. I went with a language instead of a framework. I taught a class trying to introduce these concepts, and the students were able to cheat by modifying mutable data structures and things like that. That the information was only supposed to flow certain ways, but if your language allows it, then you don't behave as well. So language instead of a framework, and I really wanted that dynamic feature because it's something, I guess, that was just in the spirit of how I worked at my work, that you would put together a simple system, and then if tasked to do some different job, you'd spin up the parts you need to do the job and tear them down at the end. And so I was really excited by the way the original FRP, the Fran from Conal Elliott, had a switch operator. But I was excited by it because it was a declarative way to describe changing it. The reality, though, I'll get to that in a few slides. The syntax, the user experience, I didn't think was as good. And so my goal is to put together something with a workflow like this, that you have a program in a language of its own, this Thorium language, and it will entail or contain some declarations, some bounds, although the bounds are specified on the command line, and then some number of properties that you wish to be true of the thing that you've described through these declarative declarations. the workflow is that it will negate the properties. It does this because if you can find a flow through the state space of the system that is the opposite of the property and is also something that declarations allow, then that gives you a counterexample. And so that then can be presented to the user. And although I did ask the question about how do we interpret counterexamples, it is at least better, I felt, than expecting programmers who might be able to specify their program to be expected to write proofs of the correctness of their program. So all right, the approach. I mentioned that there was this notion of a switch statement, and that the idea there was that any reactive value could have, you could have a reactive value made up of reactive values, and it would swap out the definition of that thing. And that is powerful enough, of course, to do a great deal. But I thought, all right, what if we instead bundle them up into something that's like an object, which programmers are more comfortable with, but within those objects, they have to be, everything has to be a declarative statement. It's limited to the reactive operators. But that if you want to do anything dynamic with it, you will do so by swapping out a reactor. And that has the interesting effect, which I discovered, I guess, at this phase in my development when I finally got this working, that you end up with a name for everything. So if you were to allow yourself to grow without bound, sure, if you're going to have an arbitrary length pipeline, at some point you would cease to be able to name the things because you've got a container. I don't yet support containers. Or you have a linked list of processing stages. And I have basically issued all of that for now. And so you end up, yes, with the ability to refer to everything. And at the top level, even though the internal structure might have changed a bit by swapping out one of the stages, fundamentally the top level flow continues to be the same thing. So part of it is to experiment with how well that limitation, I guess, supports real development. But then, well, we'll get to the end. But I am at a stage where it's not yet practical. So all right, the basic rules and this terminology comes from the SodiumFRP. It's a little unusual for those more familiar with the traditional, but I like the word, at least cell, because it is an analog to a spreadsheet cell. It's a thing that holds a value, and if it's defined in terms of other cells, if those cells change, which is what I say next, then it will change automatically. The stream is a stream of events. I feel like that was a change you didn't necessarily have to make. Stephen Blackheath, the creator of SodiumFRP, I think event would have been all right, but it's an event stream, and the idea was that you'd, standing in a river or a stream or whatnot, and things flowing by. All right, so something concrete. So this is my syntax proposed so far. You've got, a name for this object. The constructor parameters go at the top. Those are actually members, but they are not they're not declared here, other than to say that there will be some stream of. I use the data type unit to say that these are like button presses. I don't have a value, but it doesn't say what they're going to come from. That is defined by whoever creates you. But inside, if you're going to declare that you have a thing, an accumulator, so the value, then you're going to have to define what the rules are for updating. And I'll describe all these operators in a little more detail, but this one boils down to increment the previous value by whatever this increment comes in. Every time it has, increment has a value. One of the distinctions between this and some of the early things you mentioned, Lustre and Estrel and whatnot, is that there is that notion of the cells and the streams. And so the streams are allowed to just not have values, but cells are absolutely required to have a value at all times, which is why this cell needed to have an initial value. And then I have a couple of properties. And I believe the first one's true, but the second one is deliberately false, so that I can go later on and show you a counterexample trace. But all right, so the operators that I said it supports, there's lift and snapshot. That basically means you've got some function of base data types, ints, reals, it's all that's supported right now. and you describe or basically define something in terms of maybe a combination of cells and streams, or all streams or all cells. If it's all cells, you get a cell. If it's a combination, you get a stream, and it will sample either. This is something that's not true of the sodium, but either the current value or the previous value of the cell that you want to work with. And you have to be careful, think more or less as the previous case, to create or not to create cycles that are not supportable. So the next value, I should say the current value of A cannot be 1 plus the current value of B, while the current value of B is 1 plus the current value of A. So you can write illegal things, but when I didn't allow that, it used to be that if an event came in, it had to sample the old value, which is taken from Sodium's semantics. And you just end up working really hard to say really simple things. This is, I guess, my previous example, which I will return to. The accumulator actually looks really nice if you have no way of describing the difference between current and old value. But yeah, other things just didn't work as well. But as I say, it's all cells, they're cells. Hold is the mechanism for updating state. That's the thing that we saw with the basically an initial state. That must be a cell as well, or a constant. And then ... is to describe what will happen in the future of the lifetime of this thing that has been defined. So when those updates arrive, it will take on that value. If no updates ever arrive, it keeps the init value forever. There's a filter, which the left side of that has to be a stream containing events or not. And the right side may or may not be one. So effectively there's an inherent snapshot of the value of that condition in case you just want to turn on or off a switch. And then merge. So one of the other things about the semantics here is that all of the events occur simultaneously. Maybe two external events came in. If you had two stream inputs, if they place values on them and then call your run, then I guess they could make them simultaneous. But even if they aren't, if you have functions of your input, then and those are event type, then they will be simultaneous. And there might, as there often is, some need to resolve priority or handle the case where two of them are active differently from the case where one of them is active. And this just allows you a way to do that.
So you say that all the inputs are always present?
No. Any stream input is optional at all. Like any stream value is optional at all times. No, I was just saying that any event that is active within a transaction is treated as simultaneous. No ordering, regardless of the topological order of the expressions. And so this operator is just important, that there be some way of describing that merge. The approach is that when you do not have subreactors, the case that works reasonably well, actually performance-wise, you create a single trace. So that trace contains all of the members. Basically, if it was a cell event or a stream, I shouldn't say that. If it was a cell event, it's very easy to say. You will now have an aggregate data type in Z3 is the SMT solver we're using. It will have an int data type in there. If it is a stream, then it will be a stream int, which is basically just a maybe, if you use the Haskell term, so that the SMT solver can check for the presence or absence of the value. And every sub-expression, and this was a simplification for my sake, it may not have been a good one, is also expanded out so that, I think that's there, so that if you need to, you can look at the values of the sub-expressions within a trace. But if you've done something particularly foolish and obviously foolish, you won't need to see the internal state to understand why it has gone wrong. But then you will specify some number of steps and then a property, one of the potentially multiple properties you declared that will be checked in this run. The SMT solver, as I said, flips inverts the sense of the property. So if the property is that the value will not exceed 10, then it says the value will exceed 10. And then, more or less as it was in the diagram, if it can't be satisfied, great, you report to the user only that it will not be satisfied in k steps. And if it can be satisfied with the inverted property, that means that you found a counterexample. And so, yeah, I do want to say this. This entire approach, this way of doing a bounded model checking, the advantage is that even properties that might have been, say, undecidable in general, things tend to be decidable on any finite set of steps. And so we can basically just feed it into the SMT solver and it will give you these answers even if you couldn't write the proof. And so that is what I'm targeting. But a trade-off that I've made is that because it's finding a counterexample in a finite number of steps, that's the definition of a safety property. And there are lots of important safety properties, but there's also liveness, the idea that, the classic one with an elevator, if you push the elevator button, eventually the elevator will come. And honestly, you're not usually satisfied with that answer either when you're dealing with LTL, because it really doesn't say much about when eventually might come. But we will say nothing. Once we reach the end, any unsatisfied, let's call it obligation, is assumed to become true. So that's necessary for handling things like globally. So globally means at time 0, if you say globally this is true, at time 0 it must be true and every time afterward. Well, one way of defining that is to say that globally 0 is true if it's true at 0, and if globally true is true at time 1. And so on and so forth for time 1. Eventually you reach the end of the limited number of steps and you have to say something, and the something we said was what's called the optimistic semantics, and that really eliminates the utility of liveness properties at all. Everything ends up being satisfied. But all right, so back to this example, we can understand it perhaps, depending on how quickly I went through it, but perhaps a little better. We can understand that it's going to start off with that value at 0, and then when the increment button press, if you will, valueless input arrives, it's going to kick off that at, and I did forget to mention the syntax for that, sorry. That's another version of a snapshot, but a snapshot where you are not doing any math on it. So 1 at the event of an a unit or a valueless thing occurring creates this stream of integers, which are the increments, and then basically whenever the increment comes in, the value is going to go up, and so it should be clear that that claim I made at the bottom, that globally, meaning for all time, the value will be greater than or equal to 0, that part's true, and less than or equal to 3, and that's not true, assuming we test it with more than 3 steps. So I did, and I end up with this as the output. It currently does actually output optionally LaTeX, so it actually does look like that, assuming you look at it through a LaTeX viewer. And what it is telling you is that, and honestly it overachieved a little bit, but it basically just said if the thing is just constantly on, we exceed our limit. But this is where I got to that question. I was like, how do you interpret it? Because I don't currently highlight the point at which the property is not true. And in this case, it feels like it would be really obvious how to do it. And in other cases, it's not as obvious. LTL expressions often capture what you mean, but they don't necessarily do it in the most straightforward way. And so I do not yet have a good answer for how to maybe point a person in the direction to say that, yeah, your problem is that that you kept incrementing too often. And basically, it went bad at this point. So we can see that, sure, it went bad here because we know what we're looking for, but the statement I actually made was that it will globally be between these two values. And that was false at time 0. And so the property is actually false throughout, even though the sub-property that made it false became false later on. And so, yeah, it's an unsolved problem for me, how best to fix that. And there's something I cannot possibly fit onto a slide, which is every sub-expression spelled out, showing how it got into the state that it got into. Even in this case, it grows bigger than what can be shown on a slide. But all right, so sub-reactors. Same basic operation, and to the extent possible, all of the processing and the logic is the same, with one change. That any expression that can produce a reactor is treated quite differently. If the reactor took a stream as its input, I'm not going to, as I would for my snapshot operation or my lift operation, take its current value. Instead, I'm going to allow that stream to be captured and used as the input, the continuously changing input to the reactor. But the other thing that I do is that in the model, that's next, I do not store this entire reactor. So if a reactor can be created at time 0 or time 1, then I will create a new numbered reactor as part of the model building process, put it into an array, and then put the number in the slot. And so that number ends up acting as a pointer, so that you can then swap them out during the rest of the processing using the same hold logic that you would have used otherwise. So basically, it's an integer, but now if the hold would be active, then the integer value goes in, and you keep it. And then when it comes time to interpret, what does it mean to say stage 1, which we'll get to, dot out? Well, that now means the 5th item, if you will, in this container somewhere. That that reactor's out is the out of this expression. So that made it easy for me, and I think that's probably where I went wrong in this exercise. So the property is checked as above, but it can't be satisfied. The counterexample trace is shown for all the reactors, which of course is both necessary and potentially even more confusing. So I have this here for completeness. I'll go back to it if I need to, but let me just go forward and show you what I'm building. So this is the first thing that I put together to test out the new code that could handle this case, and I didn't expect it to be a problem. I thought it'd be fine. I hit go. And I waited, and I'm going to assume it was about an hour later. I'm sure I killed it the first few times that I ran it, but I do have numbers, and many times it runs taking an hour just to do this simple problem. And I don't have it here. I do need to show that to show it, but the bounded case in the bottom is to say that if no single update, I'll describe the updates in a bit, if no single update is greater than or even equal to 10, then the output won't be greater than 100. But there's 3 of them, so yeah, that's totally not true. Any 2 of them, that would be true for, but once you add the 3rd one, it is possible to, say, configure it with 999, and the product of that will be big enough to violate the rule. The behavior here is that we have the input. The first stage will multiply the input by whatever it was configured with when it was created. So it starts off as just a pass-through of the input equals the output. But if we get this config input, so there's a lot of syntax I've not gone into, but if we get this config type, it is of a type that can contain 3 different cases. Effectively, it's a sum type. So 3 different cases, one for configuring stage 1, for stage 2, and stage 3. They can come in any order. But the reason I did this was to simulate the idea that they could come in any order. And honestly, the thing could configure stage 1 all 3 times. That won't violate anything. But I wanted to allow it because it seemed like the sort of thing to do. And as I said, it ended up being far slower than I would have expected. But the idea would be that if the config comes in and it matches being type config S1, then that value C will be made available to a subsequent expression that builds a stream. That is what I'm doing with the slant, is to say things that are streams. There will be a stream containing this mult, this instance. It's really just the integer pointing to where it is in that storage. That may, and in fact whenever it's active, will arrive and stay in S1. And the fun bit is that the way that I've implemented it, if S1 is swapped first, no, that's not interesting. If S2 is swapped first, then it will depend on S1.out. If you then swapped in S1, some systems, maybe all that I'm familiar with, would actually require you to redefine S2 again, because the old one you made was listening to a different object. But here, when it says that statement, S1.out, it means whatever my owner's notion of S1.out is. And so when you swap S1 out from under it, it now takes on the old value. And so this is what I was saying about everything gets to keep a name, and we can't end up with linked lists, which is too bad. It is a limitation on what you can do. But it does mean that you know what you're talking about and you do have a name for everything. But as I said, yeah, it took way longer than I expected, so I scaled it down and realized that, for the smaller problems, so scaling it down was a manual process of cutting out the 3rd stage and running the same operation, but only 2 stages, and there it wouldn't exceed 10, so on and so forth. Very quick for the smallest case, and then, exponential growth, but not just exponential growth, since that's expected to a certain extent, but really slow exponential growth. And maybe I'll go a little bit into why that is. Well, why I think that is. But the next thing I tried, and as far as I got for this project, was to make simpler versions. So the baseline had the S1, S2, S3 configuration type, but it put them into just some coefficient numbers. And then the output was equal to those three coefficients times each other and then times the input. The sequential stage insertion took away the ability to do them in arbitrary orders, and it did help, but not all that much, which is interesting. And perhaps the way I described it made it so that the Z3 solver didn't know that as many of the side paths didn't need to be explored. And that's really sort of where I am. I was going to show, at this point in the slide, there we go, on the left, that's what the counterexample trace looks like. I did, to make it slightly more readable, take the numbers and turn them into the name, effectively, of the subreactor. But when you look at that for a counterexample, what you end up seeing is that, I just happened to do this, it swapped out S3 first. So the initially configured mult 0, which has 1 as its coefficient, still sits where it was. Mult 4, similarly, is one of the initial ones. And I'd have to scroll down to show it, and it's not terribly important, but mult 8 is just no longer being used. And maybe I should show it just because it's there, and that, I think, is the problem. I declared mult 8 and defined what it would do for the next 2 time ticks, even though, admittedly for this case, but even though it was not being used at all. And I think there's a good chance that Z3, with the properties that I've passed on to it, is trying to solve all of those. Like basically all the pieces that it doesn't need to find value, it's still applying the rules. And so one of my thoughts is to basically make all the rules conditional on whether or not the thing can be pointed to, or something to that effect. And that's easy in this case, but I have not considered whether or not that's something I can do practically long term. So, pop that back up. I am running, it feels like overtime. But yeah, the goals are provide hints to the SMT solver because, yeah, this is just way too slow. It's only 3 stages. Yes, 3 stages with more variety than realistic code might have, but still 3 stages. And so my thought is that, yeah, if we could flag them somehow as just not being active and tell the SMT solver there's no restriction on this value, just assign whatever you want. I can't make the value not exist once I've declared it as a holder, but there you are. Or, and I don't even know if this will help at all, but place a bound on the number of subreactors so that, I'm not interested in all those 9, I think it was. Actually, it was more than 9 possible subreactors that could occur if they get swapped out at this or that time. If I basically just said, yeah, there are 3 initial ones and you can have those and then 3 more that might get swapped in, what is that going to look like? And I worry that what that will look like will actually end up being more complicated. There's a whole bunch of rules governing which one of them is active. But because it is fewer things to fill in, it's possible that it might work. What I intended to do next, assuming as I had that I would continue to get reasonable performance, was containers and some look at basically some new syntax for how to deal with containers of reactors, either pipelines like they're shown here, or probably a lot more fan in and fan out to deal with perhaps a manager of some kind that's managing a bunch of workers. And then, finally, full circle, to bring in the metric temporal logic operators that sort of what kicked the whole thing off. The cool thing is if you can put a time limit on your property, then it's a safety property because it can be disproven in a finite number of steps. It's still possible if their deadlines are too long for you to run out at the end, but if you're willing to set enough steps versus the size of the thing, you can end up with a safety property. And so, yeah, when doing this, you have to make assumptions about what the outside world is up to. But another option, and a tempting one, is to add MTL operators as a new kind of reactive operator. And so what that would mean is you'd be able to say something like, one of you asked about, if a thing transitions from false to true, a rising edge, then that might kick off, or that amongst any other number of events that could occur, would potentially kick off an expression that would become false. If, let's say it's a keep alive or a debouncer. So if it keeps coming, then the thing can never go false, and that's great. But if it doesn't come within whatever the window is, then suddenly it'll go false. And so you can basically declare these timers that are related to your pieces, and then turn them into signals that you'll react to. What should I say? Declarative way to define a timer, and you can end up writing your reactor to explain what it will do if the outside world's timing isn't good. And then you no longer need to, in your properties, make assumptions of what the outside world is doing. See, yep, it is in fact the last of the things I plan to do. All right, like I said, I'm over time, but any questions?
Some questions? Yeah, do you have an example of formula that would be difficult to interpret? You said, it's easy to find a counterexample on your first slide.
Yeah,
first example. But,
I even consider that a hard one. But certainly, the one that I brought up over here. There we go. You can see, this does not matter. Let's see if we have out. There we go. So we can see that it got violated. So that's true. And that's actually easier for us than it is for the thing. But why? And why is a function of all three of them having been changed. And it doesn't matter that they changed the particular values that it changed to, but it might. And so that's where it gets really hard to figure out what to do with this. And having so many superfluous reactors, which in this case, it could be very clear that you'd say, it doesn't matter what was going on with any reactor that isn't at least in this list. But not every property is going to work that way. Sometimes one of them would have swapped in, impart a state change, and then now you can't swap it out. There is something potentially to be done with the unsatisfiable core extraction, which it's hard to get a minimal core, but the idea there would be if you have taken every declaration that was made and flagged it when you submit it to Z3, you can ask Z3, okay, you found me a problem. Basically, what set of assertions are incompatible with being correct? And it can't tell you that one of them is wrong in any way. All it can say is together they're all wrong. It also can't necessarily give you a minimal one. But the hope would be that you'd say, all right, something's gone wrong, and it has highlighted a lot of your declarations. Maybe that points you in the right direction, but it's not at all clear that it does so. So even though I did this, and I still think it's better than making people write proofs, maybe, but it's not solving the problem for you automatically.
So it's not that the formula is going to be complicated, it's more than it's going to have a lot of intermediate steps on the size of the counterexample to interpret.
Yeah.
It's not that the property is necessarily complicated.
Yep. That's the runtime problem, potentially. But yes, once a counterexample has been shown, it's not at all clear how best to convey that to the user.
So I'm not super familiar with the background, so maybe my question won't be super relevant, but I'm wondering why you chose an SMT solver as the backend to kind of do the verification here, compared to, say, some bounded model checker or something like this, where they traditionally are used for checking some LTL properties, and how the performance might compare. So,
given where I am, it is hard to justify, but my expectation was that I would use the real values in addition to the integer values. And I don't know that means that there wouldn't be other tools that I could have chosen. But that was what drew me to it, is the possibility of more interesting theories. Alloy, especially recently, given how long this project has taken me, Alloy has gone from not doing sequential models, let's call it, to now having a version that does. And so that's now bringing Alloy much closer to what this is. I've not used that mode, so I don't know precisely how they present it, but I imagine it looks similar. But yeah, it was just, I had to choose one. Z3 has really great interfaces for doing what it does. Let me build models like that, that stream type, that it was easy to just describe this as a value that may not have a value. As well as the match expressions on the sum types. That was relatively straightforward, just move right into Z3.
Thank you for interesting talk. So, in the last part of your talk, so you talking about, let's say, MTL for the, let's say, describing some real time.
It is. So I think it may be more general than that, but I'm only talking about the one that's time.
Okay.
So metric is the M, so metric temporal logic, and in particular, I'm used to dealing with the one that deals with intervals. I was able to monitor things that would not be complete. Yeah, that's fair. You can detect a violation of something, but when looking for all possible violations, it's possible that would not be.
I'm just
that wouldn't be
curious,
complete theory.
why do you choose MTL instead of other kind of, so let's say, formalisms for for example, on time automata or hybrid
Personal
automata?
bias. I ran into this problem, honestly, I feel like it was a misunderstanding of LTL, that there were some expressions that I just couldn't understand, why is this considered sufficient? And it has to do with LTL not assigning a truth value in between the points. And so then I found that there was a logic that did, and so I was like, that has an intuition for me. And I particularly like, although this makes it harder, the dense time and the continuous, continuous semantics, such that you don't get slight, I guess you'd call them paradoxes, like the idea that, so one of the operators is basically future 10 would mean something like within 10 hours, days, whatever. Future 10 is a logical expression you can state. Future 10 of P, whatever it is not necessarily equal to future of 20 of P. And if that confuses you, it should. That feels weird. And it has to do with the fact that the point-wise semantics doesn't work that way. And so, I really like the idea of the continuous. You treat them as signals. A lot of the terminology ends up being the same as FRP, which is a little bit what drew me into it. But that idea of a logical signal becomes very easy to process.
Thank you very much.
Let me change that. Easy to reason about, harder to process. It's easier if you can just basically say, I've got a finite number of events, and whatever happens, happens.
So you showed us your SMT backend. Do you already have also a runtime for your language?
No, of all things, I know, the most fun to play with. So whenever I execute this, I can only execute it by writing something false and then watching it build me a counterexample. That has never seemed like the hard part, but I may surprise myself there as well, that I may have written myself into some interesting corners.
Any other questions? Thank you very much.